Yes. Yes. There's one specific case that we have to watch out and remember Dalton's law for, though, and that's when you want to collect a gas over water. We all did we, meaning all the Chem 1 teachers, did a lab like that last year where you had a glass bottle that was upside down. It was filled completely with water. And it was stuck into a plastic tray, a trough. And then we generated the gas separately, and we bubbled that gas into the bottle. And up comes the bubbles of the gas. And down goes the level of the water in the collecting bottle, right? We started with it completely full with no air in it. And so the level of the water goes down. That's what I have a picture of up in here. This is just a simple reaction, something that generates a gas, maybe magnesium and sulfuric acid or something like that, produces hydrogen. So out comes the hydrogen, bubbles up. The pressure up there, oops. We don't have the world's smallest barometer to stick up in there to measure what the pressure is. How do we know what the pressure up there is? What?
You say, I give up.
Never say that. Okay, well, I'll tell you. The pressure inside of there is equal to the pressure of the air outside here. Why? Because if the pressure of that gas up there is greater than the pressure of the air, stop moving. If the pressure of the gas that's above the water up there is greater than the pressure of the air, then it will push down on that water. I wish it wouldn't do that to me. It'll push down on that water, which would cause the level of the water in the trough to rise up. But the water in the trough is not rising up. If the air pressure was greater, then it would push down on the trough, and that would cause the level of the water to go up into the collecting bottle. Since neither one is happening right now the level is staying the same. That means the pressure up there of the collecting gas equals the pressure of the air. So you can always measure what the pressure of the gas you're collecting of the water is just by looking at a barometer. You look at the barometer in the room, and that is the pressure of the gas that's up there. However, and there is a however, that is not the pure gas you're collecting. Like, let's say this reaction is generating hydrogen. Out comes the hydrogen through the bottle, through the tube, into the bottle. Because it's being collected over water, some of the water in that collecting bottle is going to evaporate. And you can't help it. It's there. So, that's what I have in this last part. There's always water that's going to be mixed. Anytime you collect a gas over water, you've got to subtract off the vapor pressure of the water to get just the pressure of the gas. That uses Dalton's law of partial pressures. The total pressure up there is the atmospheric pressure, but that total pressure has some water vapor in there too. We're doing a lab on Monday, and there is water present.
Please excuse this interruption.
The answer is yes.
The boys soccer parents
Don't
are
forget about
hosting
it.
a student tailgate for the regional soccer finals today at Bluefield Hills High School. All students are invited, and those attending will receive free pizza, hot chocolate, pop, water, dessert, and candy.
I would go there just for that.
Pretty nice.
Pretty nice.
Really nice.
Free food. It's like a full meal.
How much?
It's like a full street
Espresso.
cold and appetizer, nice water.
Don't be skeptical. Just they're being nice.
It's true.
All right. So yeah, when you're doing problems, watch for those three words that can be kind of built into the problem. They're sneaky. If you see that a problem, like you have a sample of oxygen, is collected over water, watch for those three words, collected over water. As soon as you see those three words, you know you're going to have the pressure of some of the water vapor up there with the gas that you're collecting. Now, usually the problem is nice, and it'll tell you what the vapor pressure of water is at that temperature. So you just subtract it off. Take the total pressure, like the atmospheric pressure, subtract off the water vapor. Now, water is not a terribly volatile liquid. It doesn't evaporate very much, but it does enough to give us a pressure that we have to at least know about and consider. Yeah?
Why is it not people overwater?
Well, when you, if we generate a gas like hydrogen, let's say I want to burn some hydrogen because I'm like that. If I try to collect it in a bottle that I didn't flush out and get rid of all the air, then there's going to be air mixed in with my hydrogen. If I want pure hydrogen, then what we do is we try not to allow any air to get in there and mix with it. So we fill a bottle up all the way with water, and then that pushes all the air out of it, and put it upside down, and then we collect the hydrogen up through the water like that, so there's no air mixed with it. That's the advantage of it. It eliminates all the air.
Could you use like any liquid?
Mm-hmm.
You said like about the vapor of it.
Right, yeah, because any liquid you use is going to evaporate some. Mm-hmm. Do I have, no, I don't have time left. I was hoping, let's just take a look at it. That was a Mickey Mouse question, that's super easy. I was hoping to give you this one. If we had about 5 minutes, we would have seen this. At what temperature must helium be so that its particles move as fast as nitrogen's? At 25 degrees. Okay, here's how we would do this problem. If we're talking about particles move as fast, the velocity of the helium particles would be the same as the velocity of nitrogen. That would mean that... Oh, I heard Hank's voice. I guess now it's impossible for me to hide from him, right?
Keep going. Oh, I thought you were saying it's impossible for us to keep going.
No, it's...
I was like,
If I want to go hide from Hank, then
Why
I
you
can't.
guys say it?
Look, I tried.
That's how we would set up this problem.
so you just plug in like, or,
Yep.
wait.
Actually, you don't. You square both sides, which gets rid of the radical. You divide both sides by 3r, which gets rid of that,
Wait, but you don't
and
have the
that.
pressure.
What?
Wait, you divide by 3.
He had to give you the R values.
You give it.
Divide both sides by 3r. It gets rid of that from both sides. Because they're the same on both sides.
Matter.
So it's just T over.
So it's just T over molar mass of helium equals T over molar mass of N2. Now, these are different temperatures. Because they have different molar masses, they would have... You too, thanks. So yeah, this would have to be the temperature of helium. That would have to be the temperature of nitrogen.
So temperature of nitrogen would be 25 plus 20 something.
Yes,
And
yes.
then you're finding T.
That's the unknown.
And then you're putting in molar mass of hydrogen. Okay.
The answer is 42 Kelvin.
Okay.
Okay, do you want to see a magic trick?
I have
Look,
Come over here. It's on being recorded.
Oh, no.
This would be for the pleasure of the people
No,
watching.
look, ready? There's nothing in my hand. Look.
Over here.
Watch.
I'm not watching.
Oh my god, that's gonna be so
Over here.
embarrassing.
Okay, there we go.
In my hands, I'm gonna have sand now. Isn't it so amazing?
That's magic.
I know.